Welcome to The Explainer. Today we're exploring a literally monumental shift in how we interact with the devices around us. We're rapidly moving from things we carry, to things we wear, to things that are literally becoming part of us. We're talking about the invisible revolution of wearable technology, that wild evolutionary journey from simple smart jackets straight to digital second skins.
Okay, let's dive into this. What if your clothing could actually act as your doctor? Now, I know it sounds like straight-up science fiction, but the source materials we're digging into today reveal that this is rapidly becoming our reality. We're transitioning into this era where invisible tech, embedded right in our fabrics and even on our skin, will continuously monitor, diagnose, and treat our bodies. The stakes for human health here? Incredibly high.
So, here's our roadmap for today's Explainer. We'll start with the evolution of smart textiles, then move into healthcare's flexible revolution and check out customizing patient prosthetics. After that, we'll break down manufacturing the future, and finally, wrap things up with challenges and our future outlook.
All right, Section 1, the evolution of smart textiles.
We obviously didn't jump straight to futuristic digital skin overnight, right? It actually happened in 3 distinct generations. Generation 1 was completely passive. Fabrics that simply sense their environment, like maybe recording a temperature change. Then, Generation 2 introduced active textiles. These could sense and react, like actually changing shape when you get hot. And finally, Generation 3, ultra-smart textiles. These don't just sense and react, they adapt. They're essentially cognitive systems woven directly into the fabric itself. Now, to really understand how we reached Generation 3, we have to look at a massive paradigm shift in the hardware. We're finally moving away from the bulky, rigid electronics of the past. Your heavy smartwatches and those traditional gadgets that always feel separate from the body. Instead, the focus is now entirely on flexible electronics. We're talking ultra-thin, stretchable polymers and advanced nanomaterials, like graphene, that can literally bend and deform without losing a single ounce of electrical performance. So the crucial point here is understanding epidermal electronics, or E-skin. Think of it as this ultra-thin, incredibly lightweight structure that mimics actual human skin. It uses flexible sensing components that conform perfectly to our biology, wrapping snugly right around the soft, squishy surfaces of our tissues. It completely blurs that line between biology and hardware.
Moving on to Section 2, Healthcare's Flexible Revolution.
Now, as you can see, there is some incredibly complex engineering involved in a matrix-based pressure sensor array. You've got these multi-layer layers that can generate power from just simple friction. And importantly, check out those serpentine interconnections. Those wavy, snake-like lines? That's the secret sauce. They allow rigid conductive elements to stretch and bend without snapping. It's truly skin-inspired architecture that moves exactly like human tissue. The clinical applications for this tech are, honestly, nothing short of medical marvels. We now have wearable health monitors that conform so perfectly to the skin, they provide precise cardiac mapping. We've got biodegradable internal implants, these ultra-thin sensors that map out internal organs, and then safely dissolve when their job is done, entirely avoiding the need for extraction surgeries. Oh, and we have smart bandages. Let's actually pause on the smart bandage for a second. Think of this as a doctor that never ever leaves your side. Imagine a wound dressing embedded with these flexible sensors that continuously monitors the healing process. They can detect early signs of infection way before a human eye ever could, track hydration, and incredibly, they can even deliver medications in real time precisely when the wound needs it, all without ever peeling the bandage back.
Okay, Section 3, Customizing Patient Prosthetics.
Let's move to and see how this builds. Because in the world of prosthetics, a poor fit can cause immense, debilitating pain. To solve this, researchers are developing patient-specific prosthetic liners using flexible tech. They utilize 3D-printed origami sensors, literally sensors folded with specific geometries for highly tunable sensitivity. Connected by stretchable horseshoe interconnections, they create an entire wearable pressure mapping system right inside the prosthetic socket.
And the human outcome here? It is profound. By dynamically mapping the exact pressure inside the socket as the patient walks, clinicians can design a perfectly customized prosthetic. The ultimate goal bridging this gap between material science and clinical application is unprecedented comfort, a flawless customized fit, and significantly improved clinical outcomes for amputees who previously had to just rely on trial and error.
That brings us to Section 4, Manufacturing the Future. So you can forget about traditional, rigid factory assembly lines.
Building invisible computers is all about additive manufacturing. Step 1 is multi-material 3D printing, which allows these incredibly complex sensors to be built in a single go. Step 2 is direct ink writing, or DIW. It's this fascinating technique where flexible silver nanoparticles and hydrogels are extruded layer by layer, kind of like squeezing toothpaste, to form actual circuits. Finally, Step 3 uses advanced inkjet printing to precisely drop functional materials onto flexible substrates at an incredibly low cost.
But, it's not just about printing sensors. It's about actually weaving the web. The textile industry is actively integrating these components, conductive fibers, biosensors, and ultra-low power antennas, directly into traditional fabrics. So your everyday shirt, or maybe a hospital blanket, becomes an interactive data-gathering device. This is exactly how the technology becomes truly invisible and entirely unobtrusive to whoever's wearing it. And finally, Section 5, Challenges and Future Outlook. Now, it's not all perfect just yet. Engineers are actively working to overcome 3 primary hurdles. First up, durability. If your smart shirt is a medical device, it absolutely must survive the washing machine and harsh hospital disinfectants. Second, scaling production. Moving from brilliant little lab prototypes to affordable, mass-produced garments requires entirely new supply chains. And third, power management. We desperately need sustainable ways to power these devices, perhaps even harvesting energy directly from your body heat to truly untether the patient for good.
Which brings us to our final thought. As engineers tackle these hurdles, and as our clothes and our very skin literally become computers, where does the machine end and the human begin? It's a pretty profound question to leave you with today, as biology and technology merge closer than ever before. Thank you so much for joining me on this explainer, and keep questioning the world around you.